Okay, we should be live. Um, Obviously, I require some kind of confirmation. Someone needs to collapse the wave function to let us know that we actually exist and not just bolts and brains floating in space. Hey everyone, welcome to the weekly guest interview here on Open Space on my YouTube channel. This week I've got, is it Professor Peter Woit? Dr. Peter, would you have a preference?
Um, I have a kind of a strange academic status, which is that my official title is senior lecturer.
Yeah,
So I'm not actually a tenured professor, but I am a faculty member at Columbia University, and I'm not tenured, but of a more or less permanent sort. And it's a long story, but
right.
I've, anyway, so you could.
Senior
I don't
lecturer.
care what people call me.
Yeah. So for people who don't know who you are and what you do, can you just give us an introduction?
Okay, so my original background was actually in physics, and actually I first got interested in science actually through astronomy. So when I was a kid, I was very interested in astronomy. I had a big telescope and all that, and then but then I got more interested when I was learning about how stars worked. I got more interested in the physics of it. Why are there these physical laws that govern what's going on inside a star? And so I ended up studying physics. Well, I went to Harvard as an undergraduate. Did a physics major there, and then Princeton as a graduate student. And I got my PhD there in theoretical particle physics. But the whole time, I was actually also very interested in mathematics and learning a lot of mathematics at the same time. And I was interested in kind of ideas about applying more sophisticated mathematics to physics. And then I was a postdoc at Stony Brook after Princeton for a while, and then that was when the whole kind of string theory thing started kind of 1984 while I was at Stony Brook. And by the time my time was up at Stony Brook, it was pretty clear if I wanted to stay in physics, you really, traditionally there aren't very many jobs in that field, and the very few jobs there were really going to string theorists, especially if you were interested in math. So I ended up deciding it'd be better to try to get a job in a math department. I ended up getting a postdoc. I ended up teaching calculus 1 year at Tufts, and then getting a postdoc at Berkeley and at the Math Institute there, and then ended up at Columbia over 30 years ago, and I've been here ever since. And so my interest remains really in the particle physics and kind of how to approach it and see if we can find some new ideas about it mathematically. And so one thing that I did that got a bunch of attention was about almost 20 years ago now. I started writing a book that ended up being called Not Even Wrong, which is about the state of particle theory and particle physics at the time, and which I actually think it has held up very, very well.
Yeah.
If I
Yeah.
do say so myself, considering what's happened over the last 20 years. And then more recently, every few years I've been teaching a class on quantum mechanics for mathematicians. And I ended up writing a textbook about that. And this semester, I'm doing the same thing. I'm teaching this class. So I'm here later, 4 o'clock later today. I'll be teaching on this Blackboard to the students remotely. I'm also having a version of lectures for that course now on YouTube if people really want to follow them. I also very recently, last year or so, I've finally something, after many, many years of trying to do very kind of ambitious things, ideas about some new math for physics, and finding that the more and more I worked on some idea, more and more clear it became it was a bad idea. I finally found one that actually seems to be working very well. So I'm very, very excited
There's
about
got to be
some.
something wrong with it then.
Well, so far so good. And so it's an idea about anyway, I would probably better to not get started on that, but it's an idea. Part of it involves some ideas that were due to Roger Penrose about twistors, about a different kind of geometry for thinking about space and time. So
Mm-hmm.
part of it involves that. Part of it involves the idea that you really some ideas about time. There's kind of a technical thing about time in our theories about how you treat time. Sometimes it's a good idea to make time a complex variable, and then look at imaginary time, and then all of the your equations all of a sudden behave much better. And so that's related to what I'm
Right.
pursuing.
So,
But maybe that's the outline.
yeah, well, I mean, you came across my radar back in, I think it was 2006, I think was when you first when the first
That's
published the
when the
book.
book was published. Yeah.
Yeah, Not Even Wrong. And And it was interesting because at the time, string theory was all the rage, and had been all the rage for already 20 years at this point, as you said, back into the 80s and 90s. And yet it clearly wasn't being productive, like from a answer the deep, for combining the fundamental forces of the universe. There were definitely some really interesting mathematical strides that were going on. So before we kind of dump on string theory, have there been some benefits to it?
Well, I mean, there's certainly some very interesting things in mathematics have come out of it. And this was actually true from the beginning. And I think one thing that seduced a lot of people early on was some of the mathematics that was getting used and the mathematical ideas. And I think it also is what made it kind of impossible to kind of work on mathematics and physics and not work on string theory, because that was where all the attention was going. The problem always about that, though, from the beginning was that the ideas that were showing up in string theory that were really kind of beautiful mathematically and were leading in interesting mathematical directions, they always were kind of orthogonal. They were always headed in an opposite direction to the ideas about making contact with the physics. The more you tried to make the theory look like physics and agree with some, with something we see, the uglier you had to make it. The more you try to pursue something beautiful, the more it stopped looking like physics. So I think a lot of really interesting math has come out of it. Some other physics has come out of it, but I think pretty much all of that has been kind of, when people have gone in a different direction than in the than in the direction of trying to make contact with particle physics and reality.
Yeah, I mean, obviously I'm just a journalist, and my sort of what I kind of hear is that the math that's been used to develop it has been helpful in helping to untangle other fairly interesting physical problems, but as you say, kind of orthogonal, not directly connected to the original problem, and it doesn't help to answer the underlying question that they're really seeking here. And so then you wonder, does all of that time and all that mind power that's been spent to develop this interesting mathematics, could it have been better spent with other investments in directions and mathematics and so on? So do you still stand by sort of your position of 13 years ago that it's...
Oh, yes. I mean, I think the only thing, a lot of the point of view of the book was really that, the field is really kind of a victim of its own success, that we have this incredibly good standard model, and it agrees with all the experiments pretty much. And so people don't know where to turn, and that a lot of the interest in string theory was kind of an artifact of people not being able to make progress on something more promising, because there just wasn't the kind of experimental anomalies to pursue. There wasn't wasn't much place to look. And at the time that I wrote the book, that was before the LHC, and so the one part of the standard model that still hadn't been tested at that point was the existence of the Higgs particle in a Higgs field. And so the fact that the LHC found a Higgs particle with more or less exactly the properties expected, that actually, I think, just has in some sense made the situation worse in terms of a victim of its own success. So I think, I myself and a lot of people were hoping that the LHC would not find the Higgs, that it would find something, that there was some other different kind of mechanism causing this thing to happen, and then that would give us a clue as to where to go. But that didn't happen. And a lot of the speculative ideas motivated somewhat by string theory about supersymmetry, that there'd be these exotic superpartner particles found, and there was a lot of claims that these things would be seen at the LHC, and none of that has appeared. So there's been kind of a twofold, I think, intensification of the evidence for the problem that I was trying to point out there as the main source of the problem where we are now.
I mean, it's almost the worst possible outcome which is that you got this situation where there was this final particle to bolt into the entire standard model of physics. The LHC was designed not only to find that particle, but also to help push physics to whatever is the next step, because clearly you still can't put gravity and quantum mechanics together, so there's got to be more. And the LHC, the hope was not just find the Higgs particle, which I think had been hinted at by other particle accelerators at this point.
Well, I mean, the evidence up to that point was very indirect.
Right.
Really, yeah. So it's and we knew on theoretical grounds that something had to be causing a certain thing to happen in the theory, and the simplest way to do it was to introduce this Higgs field, and some very indirect measurements were consistent with that being what's going on. But that was all we had. You could reasonably hope that we were missing something, and that there was a different, more interesting way to make this happen. But doesn't I mean, if there is, you can't see it at the LHC energy yet. Maybe at higher energy.
So where do we go now? And I think this is, again, as a journalist, I depend on you and Sabine Hossefelder and all of these various physicists for some kind of analysis of where everything is going. And it does feel like there's a bit of a schism. On the one hand, you've got some people planning whatever comes next after the Large Hadron Collider, some super collider, but without any specific goal in mind, just start smashing things at higher and higher energies to see what you get. Hopefully something will crack, and that will give you a hint at what's the right path to go. And the other strategy seems to be to just go back, probe the edges to find what is a more useful direction to go before laying down the billions of dollars to build that next mega science experiment. What do you think is the right course of action now?
Well, I think it's a very, very difficult situation. So where we are now is that the LHC has been turned off for a while, partly because of COVID, partly because they're doing some upgrades and improvements, and they're going to be doing some more over the next few years. And it's probably got another 15 years or so before, during which they'll accumulate quite a bit more data, 10 to 100 times more data, and you'll be able to look at things a lot more carefully. So that's kind of a healthy endeavor for the next 15 years or so. But there comes a time in which there is no way to kind of significantly increase the amount of the data rate this thing can do, and you running it extra years just doesn't give you anything, only marginal use. And at that point, I think the hope, what people are in this business or who do this, we're hoping is that they'll come up with some new machine or some new idea for what to start building that would take over 15, 20 years from now. But the problem has always been, and I actually wrote about this also. This is one thing I even wrote about in the book, is that there are these really fundamental technological limits on these accelerators, and they're just very fundamental things that if you how high you can go in energy with a circular collider with protons just depends upon how strong a magnetic field you can build, and then you have to build these magnets, and they have to be able to operate very, very reliably, and you have to be able to build miles and miles of these things and be able to afford to pay for them. And the state of technology is just that I think now the best magnets people have of that kind, similar to the ones in the LHC, are about twice maybe roughly twice the magnetic field. So what you could do, the simplest thing to do would be to just take all the magnets out of the LHC and put in new magnets, and you would get an extra factor of 2 in energy, but this would be very expensive. These magnets are very, very expensive. Paying for miles and miles and miles of new magnets is billions of dollars. And so that's, in essence, kind of the fight that's going on is it really worth it, I guess. In my mind, I find these arguments a little bit frustrating because it seems to me that this, I think I disagree with Sabina, because to me, a crucial thing is actually, what's what is the cost of these things? Is there a viable way to actually find that cost? And can that be done without damage to other things? And we still don't, that's still very, very unclear.
Mm-hmm.
What CERN has been talking about, all they've really done is said, the best thing in the future would be to build this very expensive new accelerator, but we don't actually have the money for it. And so we're going to keep studying it. I mean, that's really all they've said at this point.
Right, right. So that when, but I mean, I guess there's two parts to it, right? There is the accelerator, the ability to speed up particles, and then there are the instruments that are looking to detect the outcome of the collisions. And I mean, I can't think of why you wouldn't, like in every scenario, you're going to need an accelerator. And then what experiments you bolt onto the accelerator can be flexible as the theories evolve, right?
Yeah, well, I mean, these detectors that people build for this, I mean, that's also there's a very sophisticated things. They've been doing this for a long, long time. And to some degree, they're tuned a little bit to what they're looking for. Like, they were, some of their design is based upon, they know that, okay, we're looking for a Higgs particle and it's going to have roughly these properties. So our detector should have these things. But they're also very much also designed as kind of fairly general purpose instruments. I mean, the idea really is that, if you build a new accelerator, it's got 10 times the energy, you can all of a sudden kind of see things of 1/10 the size. And, and you build a very general purpose detector to just kind of, in some sense, see everything that's coming out of there. I don't think, I haven't heard of any kind of viable ideas for, a different kind of experimental apparatus. I mean, what people would like to do is to try to find some way to not actually need, to produce these very, very high energy beams, to find some kind of way of studying physics at these shorter distance scales, without using these high energy collisions. But it's the only ideas about this, again, they're very, very, they're ideas for getting very, very indirect information, which is then, even if you learn something new, it's going to be very hard to interpret what it really means. People really it's a very tough position, and there's kind of no easy way around
right.
it.
Yeah. I mean, I think about other mega experiments, but they're on the observational side. So I think about things like, say, the ice cube experiment in Antarctica, where they're going to be, it's a kilometer of ice today. They're planning to make a version of it that will be 10 kilometers and be a lot more sensitive to detect neutrinos. And you can imagine continuing to scale up that experiment bigger and bigger. And essentially, because those more sensitive neutrinos are out there, the more you make ice cube more, able to detect them, the more interesting things that you're guaranteed to find. You're just going to start detecting supernovae. You're going to start detecting neutrinos from other stars. Maybe you're going to get to the cosmic background neutrino. I don't know what the term for that is. Background, I guess. And then another example of that would be something like, say, these gravitational wave detectors. I mean, you had LIGO, and then you had advanced LIGO, and advanced LIGO is turning up a gravitational wave a week. And then you look at some of the bigger versions, and maybe they're going to start detecting, and it's possible within our capability to essentially detect every black hole collision within the observable universe. You build the Big Bang observer, and now you're able to go after the primordial gravitational waves of the Big Bang. Like it seems like, while with the Hadron Collider and with the ultimate versions of that, you're the one having to produce the particles as opposed to just listening to what the universe is producing. So is it time to focus more on detectors and telescopes than attempting to generate them ourselves?
Well, I think the thing is, it's just getting at very different physics. The problem is, and I think, the things you mentioned are much. So that's a much healthier field. That's kind of observation. But what you're really learning about, mostly what you're learning about is, you're learning about, what's going on with how many black holes are out there, what are their general properties. And the problem is that you're not really learning anything new about, what's the physics happening at, at smaller and smaller distance scales. The problem is you don't see, it's very hard to get any new information about that way. You can get lots of information about what's going on in the universe, but and part of the problem, so for instance, if you try to do something like IceCube, you do have some very, very high energy neutrinos coming and colliding in the atmosphere or maybe in the ice or wherever, and you can look at the products of that collision, but the problem there is just that the numbers are very, very small. There's some vanishingly small, I don't know, dozens or hundreds of events they have that are up at the energy scale where you'd start to get to you'd be looking at similar processes in the LHC. And the problem with particle collisions is basically almost all the time nothing interesting happens. In some sense, if even when you collide two particle beams at the LHC, there's this vast, huge amount of collisions of stuff going on, but almost all of it is kind of glancing blows of one beam off the other. And it's producing a spray of all this complicated stuff, but it's not actually telling us anything new about shorter distances. So the LHC detectors are, a lot of their whole design is to find, the 1 in a trillion or the 1 in a billion event where things got close enough to actually interact in a new way and to see what happened, or they dumped enough energy in a small enough place to produce a new particle. And the problem is, if you've only got a few dozen neutrino events at that energy, and you're looking for 1 in a trillion thing, it's not good.
You're not thinking of the numbers that you need. Yeah. So do you? I mean, is it partly an issue of like back in the day, there was the idea of building the superconducting supercollider in the US, and eventually that was scrapped and they built CERN as well. Is there a gap? Is there a future level of energy that if you could cross it, then you could start to make productive work again? If you could magically generate the kinds of energies that were needed, or have the magnetic containment fields that can handle it, is there a place where you could pick up and feel like you could be making productive work again in the field?
No, I mean, that's the problem. The situation now with what we've seen at the LHC is that the standard model is looking good, arguably to arbitrarily short distances or arbitrarily high energies. That we don't see any evidence for a new kind of physics that would be at some other energy scale. And even, people talk about even the Planck scale, but I mean, the argument that that quantum gravity is some phenomenon that you're going to see at the Planck scale is that's even that's not so clear. So and this is, I think, Sabina's argument that, look, you guys have no argument for why, you're going to find something new, and so why spend the money? And so it is very different than the case with the LHC, where we had a very strong argument that you had to see a Higgs or something like it at the LHC. So so if you anyway, but that's the fundamental problem, that if you it's expensive, and we don't, we can say that, if we do this, I mean, I think the positive argument for a new collider is that, look, we can maybe, if we spend a lot of money, there's we can kind of go a factor of 10 in smaller distance scale over what we know, and we can study that. It's true, we don't have any reason to be any assurance that we're going to find something new there, but hey, it's worth continuing to do science and to keep looking. And you can study the Higgs interactions, the way the Higgs works, in a lot more detail at a higher energy accelerator. And the Higgs is also a very, very funny particle. It's, in some sense, most of the things we don't understand about why the theory is the way it is have to do with the Higgs. But so far, everything we've done looking at the Higgs, it looks exactly like it was predicted. So.
But can the LHC do the work that's needed to help us understand the Higgs to the level of sort of clarity that you're talking about, or is it? I mean, do you want to go to that higher?
Just as an example of one thing, one thing you'd like to do is you'd like to ask, how does the Higgs interact with itself? If you had two Higgs particles and you try to how would they scatter off each other? How would the Higgs interact with each other? And so you can try and measure the self-interaction of the Higgs. And that's something the LHC, with all the data it can get, may make some very, very rough, I don't know, I forget the numbers, 20, 30, 40% measurement, and you could just barely see that and see if it was there, but not really have anything other than a very rough idea about it. Whereas if you went to if you build this something 10 times higher the energy, you can maybe measure it to 5% or 10% or something.
Right.
Don't trust me on those numbers.
Yeah.
But that's an example of this. That I think is about probably the most serious case of something that we can actually tell you that here's something we would learn by doing that.
Right. So where then in, I mean, it definitely feels like it's starting to border on an existential crisis for particle physicists. When I talk to them, I can definitely feel this not frustration exactly, but kind of disappointment that they didn't have a lot of interesting things happen. Like even in the world of the cosmologists in the last year or so, all of their theories are starting to fall apart. And they're really excited about this, that you're measuring the expansion rate of the universe with a level of accuracy that shows that there's some missing pieces in the model, that different measurements just with radiation are turning up to give different answers about the expansion rate of the universe. Like it's a really fertile ground now, and the cosmologists were, I think, in a very similar place to where the particle physicists are, and now they're giddy with the opportunity to look at this. And I always find that so funny when people, like, there's nothing scientists love better than to find out their ideas are wrong, because it's just like so much new fun.
New things to think about. Yeah, I mean that's really the whole problem with particle theory. Just theory is too good. We haven't found anything wrong with it. It's very, very, very frustrating.
Yeah. So then where do you think is the fertile ground at this point?
Well, so my other argument was also partly an argument of the book, and partly, what I spend my time thinking about. My feeling has always been that, and this is one thing that bothered me about string theory. I thought string theory was just kind of a huge distraction, that we had, we have this incredibly successful theory, even more so now than 20 years ago. And so we should, to my mind, we should be focused on trying to understand it better and think about, what are the things that are going on in this theory that, we don't seem to really have a reason why they're there, or, and also just mathematically, it's true there's some interesting mathematics came out of string theory, but there's also just an incredibly beautiful and incredibly deep mathematics going on in the standard model. And there are these mathematics of gauge fields, of spinors, of the Dirac equation, and there's this kind of striking fact that some of the deepest ideas that mathematicians have turned up over the last century have ended up being, that they're exactly the same thing that physicists found on their own when they were studying, the ideas that led up to the standard model. For instance, the Dirac equation is a crucial thing in the standard model, and mathematicians who were studying another kind of basic thing about so-called index theory, the relationship between topology and analysis and differential equations, they kind of they found that there was this kind of crucial object that played a crucial role in the theory, which they constructed, and they're very proud of themselves. And then somebody pointed out to them that that's the Dirac operator.
Right.
So this thing happens time and time again in mathematics. So to me, there's just there's still a huge amount of opportunity at the interface between new mathematics and the standard model. We now have been looking at this for long enough that we know that you're not going to do something really, really new. You're not going to solve the problem of the standard model with some well-known mathematics. It's going to require some new mathematics. But I mean, to me, I see plenty of reasons to believe that, there's both kind of new mathematics and new ideas about the standard model that are there. And this is one thing that I've gotten excited about recently. This twistors are one example of the kind of thing I have in mind. But it's a purely so it is possible to, wait a second. Hi, are you still there?
Yep, yep,
Hi.
yep,
Sorry, I just got something appeared on my screen. I don't know why.
yep.
Anyway, so it's possible to make progress on that without having new experimental input. And in some sense, I keep telling physicists, look, if you guys want to figure out how to make progress in particle physics when you don't have new experimental data, go and talk to mathematicians and see what mathematicians do. We've never had experimental data.
Right.
So there's a very different kind of culture among mathematicians about how you make progress. And there's a very different ways of kind of proceeding and just a different sociology, a lot of which is based upon the fact that you can't rely upon some experimentalists to come in and tell you what the right direction is to go and whether your ideas are right. You really have to yourself come up with new ideas about where to go and yourself be sure that your ideas are actually correct. And this is one reason why mathematicians are so interested in proofs.
It's interesting. I mean, my education specifically is in computer science, and we have sort of two flavors of it. One is the mathematician side, the people who are working on the algorithms and the proofs for new methods of computation that may never be run by a computer ever, and yet they are sort of trying to explore, P versus NP and things like that. And then on the other hand, you've got people who are working on very practical algorithms that are designed to search and sort and scan and to be able to run neural networks and so on at faster rates. And they have this very practical uses in our daily lives. And I think that side, the purely mathematics side, is a very difficult road. Like, I've always really avoided it. There's the time when I spent doing mathematics that I really enjoy that process of coming up with a proof, but I still want to be able to look at the answer sheet at the end and go, did I get it right? And yet when you're in unexplored territory with mathematics, there's no place to go and actually see if you got it right or not. How do you stay motivated? How do you stay, I don't know. It would be really difficult for me. I don't know how you and other mathematicians can stay in that space and make progress and not go crazy.
Well, I mean, different people enjoy different things. I can only speak for myself, and I've had kind of a weird career that I've written very little in the way of papers. I've just been, and partly I have the strange job here at Columbia, and so I've just spent just a lot of my time doing what I enjoy most, just because I enjoy it, which is kind of learning about new kinds of mathematics and seeing how it possibly fits together with ideas about physics. And so I've actually, most people, the way their careers are structured, I think focus much more on becoming experts in some particular kind of calculation or problem and stick to that and try and push this one small area further. And a lot of people enjoy it, and that's what their career is. Mine has always been just kind of wandering around trying to learn new things and convincing myself for a while that, oh, this is a great new idea and I think I can do something new. And then after 6 months or a year, whatever, realizing, no, actually, it's not such a great idea. It doesn't work for this reason. But it's anyway, yeah. But it's true. You have to really. It's a very different sort of rewards than kind of having specific results which you can compare to experiment or the real world, or you can engage with the real world. You're really and at least to my mind, because of the problem that the physics itself has been very static for the last 30 or some years. I mean, it's the standard model. I mean, that's the thing I think about it, and it really hasn't changed much, other than we've found out that there is a Higgs, but the kind of the different kinds of mathematics you can think about as being better ways to think about it. I keep finding new things which look promising and which look interesting, and so I find it myself in a funny position, at least. Personally, I see many directions at this point where there's interesting things to think about, and there's interesting kind of things that would involve developing new mathematics and that quite possibly would tell you something new about the standard model. But getting anyone else interested in them is becoming increasingly difficult, because even when to some extent, to a large extent, the people who are doing string theory have kind of abandoned string theory, but they've kind of abandoned string theory without kind of admitting that this was not the right direction. So they've kind of headed off into doing other things, but they're still kind of, the way they talk and the way they motivate everything and the way it is all kind of based upon acting as if string theory was a good idea that worked. And so part of my kind of, well, also there's also my blog, and my book was partly an idea that, okay, well, I'll just explain to people why this doesn't work, and then people will drop it and do something more interesting.
Right. And how'd that work out for you?
I think I've had some success at getting people to realize, well, yeah, this actually doesn't work, but it's been kind of frustrating. It's been hard to convince them to pursue anything else that I'm interested in, that people have kind of just kind of pursued they're headed the same direction, which to me was the wrong direction, but they're headed the same direction that they always were, and just getting farther and farther away.
Yeah, I mean, it sort of feels like you sort of ruined string theory Christmas, but without providing an alternative that people could really hold on to and make a lot of progress. And so I think you had a lot of people go, yeah, he's probably right, but what else are you going to do? What else are we going to work on, Yeah,
and I'm in this funny position now that just in the last year or so, I actually, yes, I've been always very aware of that criticism, and that it's perfectly valid criticism, but actually now I'm actually starting to feel like, wait a minute, I actually have this very specific idea, and I've written a draft of a paper about it. I'm writing some more stuff about it. Hopefully be done soon, but I think I can point to something, but it's very different than what people are used to thinking about, and we'll see. I'm hoping that, as I understand the stuff better and do a better job of explaining it to other people, I'll start to slowly get some more attention. But it's just very different than what people are used to doing.
I mean, but it does feel like it was a dead end that a lot of people got trapped into for decades.
Yeah.
And putting on top of that, you've got it does sound to me like there was an institutional academic flow that was pushing down towards that cul-de-sac that people were getting caught up in and flowing in the direction of the string theory cul-de-sac. And now, if you were a really self-starter, really clever person, really powerful mathematician, you could go in another direction and people could go, well, we're just going to let you do your thing. But if you were, if you wanted to make progress, that's where the money was, that's where the funding was, that's where the connection to some of the experiments were, going. And so it was hard to run against the stream. Now, is it hard to go against? I mean, is there still that same current moving in that direction, or is that current dissipated at this point?
Well, it's different. I mean, one of the things that really struck me about the different sociology of physics and of mathematics is, mathematicians, partly because of this awareness that you don't have experiment telling you what to do, they've always been people have much more of a tendency to spread out, that people do not want to all be doing the same thing. And if there's some big new theoretical development, somebody has some really good idea or proves some great new theorem, it'll attract some more people to work on that, but not a huge number. And there's a lot of respect for the idea that, just because something new is happening over there, to really become expert at it and do something really good, it would take years of devoted to it. So, that's something. It's not like everybody should just go and jump on it and start working on that tomorrow. Physics has always had this different kind of sociology caused by the fact that, that for decades they would turn on a new accelerator and these new particles that you didn't expect would pop out, and you'd have all these new measurements of them. And of course, everybody would just drop what they're doing and start thinking about that. So it's really kind of, theoretical physicists are much, much more focused on, what's the hot new idea. They'll spend all their time on the archive where they're looking at what are all the new papers and what are the top people, the top places thinking about, what are they doing. And so there's this huge force pushing everybody to kind of to identify something as, okay, this seems to be a new idea, let's all work on it. And then, and it's not just that, well, you're going to get more grant money, you're going to get more jobs. It's also, you want to do that because there are going to be other people to talk to about what you're doing. If you decide to go with something else that everyone's interested in, you've got nobody to talk to. Whereas if you decide to take an interest in this latest, hottest, somewhat faddish topic, then, there's all these interesting people to talk to and all this stuff to do. So it's those kind of forces have been going on. And the problem is just for a long time now, they've been kind of decoupled from, this experimental impetus, which kind of at least was told you that this is where you got to look.
Right.
Now it's like people are just doing it because, anyway, for purely kind of sociological reasons.
Right.
It's
I mean,
really...
in the earlier stages of particle physics, it was like there was just like a mystery box of interesting puzzles thrown out on the table every day, and people got to pick through them and go off and work on them. And now there's very few left that are there that you can actually work on. So what advice do you have for people who are maybe starting their career, who are in university or, moving towards becoming a grad student, and they're trying to find their place in, I guess, a time of uncertainty for the future of particle physics? Where do you think people should focus their time to have a long and productive career in this field?
Well, I mean, if you're interested in specifically the kind of problems that I'm interested in, I often advise students that you should seriously consider, getting a math PhD rather than a physics PhD, because, it is a very different culture. You're much more likely to be able to work on things which are not so faddish. And anyway, there's I think there's an argument for, in certain cases, for that, if people are interested in that. I mean, but if people are not that interested in some of the pure mathematics, the way it's done, then then this isn't so good for them. But it's it's very hard. I mean, as you say, though, I mean, there are kind of areas more related to astrophysics or gravitational radiation or cosmology. I mean, there are areas of of different kinds of fundamental physics which are much healthier, and so the but I think this is what you already see happening. I think a lot of the best young students are not going into this field. They're going into these other subjects, or they're all of kind of quantum between quantum computers and quantum computation. If you're interested in quantum theory, there's a lot of money and things to do pointing you in that direction. So I'm afraid that really what's going to happen in particle theory is, if something doesn't change, we'll just kind of slowly see that. I mean, the field will just become it'll remain fairly narrow and just get a bit smaller. It's hard to say, though. The weird thing is that people in this field kind of keep complaining about, grants have gone down, money is hard to find, and it's actually not really true. What's actually been true for the last for quite a while is there are a fair number of wealthy people like Jim Simons and Zuckerberg and Milner who actually put some serious money on the table, for a high profile theoretical physics, and so there's anyway, while NSF grants may be going down, there's other sources of money which have been going up, and so
it's interesting.
The problem isn't really money. It's really kind of intellectual health of a different kind.
Yeah. Well, my recommendation, people always ask me how, they want to know how to get into the field of astronomy. And my recommendation is get a computer science degree, because really telescopes at this point, it's all computer science. Like you're learning to make a telescope is just a big robot, and you're programming it. And then it's putting out data that you're then analyzing with other robots. So, but then, maybe I'm a little myopic on this, but it feels like all fields are just collapsing into computer science.
Well, I found, I mean, having those skills is certainly very, very useful. Actually, my PhD in theoretical physics, I was doing Monte Carlo calculations of quantum field theories. That's how I started out. So I also and that kind of background has sometimes been useful,
Yeah.
but it is very different.
So I want to, and I know there's some people watching. I want to get some chance to get some questions from the audience as well. So this question comes from Neil Yu, and he wants to know: is there any way to make antimatter more inexpensively to power our future interstellar spacecraft? Because right now, I think it costs like something like $62 trillion a gram to make antimatter in
Yeah.
particle accelerators. Could we ever build an antimatter factory?
Anyway, I don't have any idea. I mean, the fundamental physical problem is that the only way to make antimatter is to, if you don't have any, is to kind of dump enough energy in one place to pop out a matter antimatter pair, and then separate them, and then somehow can do something. So that's the only way to do it. So you've got to anyway. So you've got to dump a very, very large amount of energy in a very small place, and then you'll start getting this to happen, as well as all sorts of other undesirable things. And so it's a very it's I don't know. Somebody may someday have a very clever idea, but it's a very, very hard.
So you've got to do those two things of getting an enormous amount of energy into a small field, into a small area, and then you've got to be able to keep the particles and antiparticles from reintroducing themselves to each other. If you do those two things, your factory is ready to go.
But the main thing, But so in some sense, I mean, in our modern theories, you should think of what in some sense, maybe one way of thinking about the way we think about the world now in these theories is that the fundamental thing is the vacuum. There's this vacuum here, but it's like a body of water or something. You can bang on it and create ripples, and particles are just kind of are kind of ripples in this, and so you can create particles by banging hard enough on the vacuum state, and if you bang harder, you create more and more particles. But if you want to create particles of a certain mass, I mean, the problem with antiparticles is, if you want an antiproton, you've got it has a GeV in mass, so you have to dump 2 GeV into a specific place so that you'll produce, because you can't just produce an antiparticle. You can only produce particle-antiparticle pairs, because you have to have a conservation of charge and everything. So you have to produce an antiproton and a proton together. So you've got to bang hard enough on the vacuum, basically, to have 2 GeV worth of energy in something the size of a proton. It's really hard to do.
But I mean, just like if you just like went the Elon Musk route from first principles, the lowest possible cost would be to generate a GeV of energy in a small space. Like if you could, like whatever that price is to do, that would be your absolute bare minimum cost to produce antimatter.
Yeah, and that's So I think, I mean, there are the ways people are doing it, and so for instance, actually, what is it, the previous machine to the Tevatron, to the LHC, the Tevatron at Fermilab, that actually collided protons and antiprotons, and so they actually produced lots and lots of antiprotons with some other accelerator banging on something, and separated them out, and then accelerated them, and then collided them with the protons. But when they built the LHC, they kind of decided that it's actually so hard to kind of produce enough antiprotons to make it worthwhile, that it's better, even though it's somewhat better to be colliding protons and antiprotons, you get again, you can kind of there are reasons why that's better. For the LHC, they decided not to take the trouble to create antiprotons, and they just collided protons and protons. But it is a well understood and standard problem among particle physicists. How do you produce antiprotons, and how do you make them, and how do you?
Well, I mean, there's one of these machines in many hospitals. I mean, there's an antimatter factory in the underground of thousands. I think 40,000 hospitals around the world have the ability to produce positrons for their PET scanners. So, I mean, it's just that you don't need many to do the job of studying a person's health, as opposed to powering your starship. So
I guess your other problem, the problem with all these also ideas about powering your starship is that the whole problem with all these things is you kind of can't, if you're going to use this to generate some power or something, you're probably putting far, far more power into producing the thing than anything you're ever going to get out of it. So,
Oh, well, I mean, antimatter is a battery,
yeah.
right? It's a compact energy form. And so it's not a source of energy. It's just a way that you store energy in a compact way. So you don't need to carry around enormous fuel tanks. When you compare the energy stored in antimatter compared to the energy stored in a Saturn V, right? Yeah, and you're combining your matter and your antimatter flow. Now it's just starting to sound like Star Trek. Let's move on. A.V. Scott and Flower asks, costs aside, would there be any advantage to building a collider in space?
Not obviously. I mean, the problem is just there's this huge amount of infrastructure around these things, but just I mean these detectors. It's not just a matter of building the accelerator, but I mean you have to kind of cool down the magnets. You have to have detectors. It's just there's just so much stuff you have to do to kind of keep this all operating that building all this stuff in space would be really there's no kind of particularly obvious. There's plenty of room. There's plenty of room here on Earth, actually.
Right.
Actually, really. I mean, I guess the only thing you could imagine that in space you would have a vacuum. You wouldn't actually need to maintain kind of a vacuum tube for the beam. But well, but not even sure that's true. It may be in space. There may be so much stuff in space that it wouldn't be enough of a vacuum compared to what the LHC uses.
I mean the. There's a couple of atoms per cubic meter, so a few dozen atoms per cubic meter, but I'm sure if you're firing your beam, but I guess with say the Large Hadron Collider or whatever comes after that, it's the magnets and the ability of the magnets to bend the path of the particles. And so theoretically, I guess if you ran a ring around the solar system, for example, at the Earth's orbit, you wouldn't need very powerful magnets to bend the stream, as opposed to having. So you could, you say there's a lot of space, but there's not an astronomical unit's worth of space. So maybe you could.
There is that advantage of scale that on the Earth, the biggest ring you could build would be one around the equator or something, and so you could get something bigger than that by going into space.
So blank check, particle accelerator that runs around the equator of the Earth. Would that answer any questions, or is it still just too undefined at this point? I mean,
the Sabina's objection still holds that we don't know. You can actually figure out the energy. I mean, the energy, with these kind of fixed scale magnets, the energy you can get scales linearly with the length of these things. So whatever they're talking about, building a 100-kilometer machine, and I don't know what's the circumference of the Earth, and it's
like 40,000 kilometers.
Yeah. So what is 400? So okay, so you get a factor of 400 in energy, but we don't actually have anything saying then that extra factor of 400 energy is going to be the right one to do something new.
Right. I mean, but even like if you're looking at 10,000 times the amount of energy, there's no predicted place. Really, yeah.
And I really take this as very, very strong evidence. I mean, the standard model is absolutely rock solid. I mean, really, it's relying upon just trying to break it is really is a really, really hard road to know. So it's better to try to actually understand, take it apart more and understand its mathematical structure and find some new ideas about new ways to formulate a theory that give you, to the extent that answer the same questions as a standard model in the same way, but may also answer some other new questions.
Do you think that, for example, things like dark matter, which is sort of a problem that is shared by both particle physicists and astronomers, do you think progress will be made more by astronomers or by physicists?
At this point, I think definitely by astronomers, because it's a, I mean, the evidence for it is really astronomical. It's from astronomical observations. We've never done any kind of particle physics lab measurement that would show us any evidence for dark matter. So it appears our only handle on it is coming from astronomical measurements, and those,
right,
by improving those, maybe we can get a better idea of what's going on.
But I wonder, like, you know, like if an astronomer came to you, and I know this is happening already, astronomers are coming and going, okay, we think that it has this kind of a cross section, this kind of a mass. Can you find a particle that matches these characteristics?
Yeah.
Are the particle accelerators able to answer those specific kinds of questions?
Well, I mean, both. I mean, the LHC is sensitive to it. It can produce, if there's a new dark matter particle, you know, so-called WIMP, that of a certain mass range with certain kinds of couplings, it should produce lots of them, and you should see them. And the fact that you're not seeing them means they don't exist. There's also other kinds of, you know, these experiments where you put like a huge, you know, kilotons of xenon down under the ground and look for something unusual to happen, and that's sensitive to a different range of masses. So none of those things have seen anything.
Yeah.
If you look at and my favorite way of looking at it is just look at this if you look at the Standard Model itself, there's kind of one part of it. There's in some sense one hole, and so in some sense if you look at neutrinos, that if neutrinos were completely massless, then one way of thinking of that is that, you know, particles in some sense come in with left-handed and right-handed parts, and if you only have a left-handed part and no right-handed part, then the particle has to be massless. So if neutrinos, the simplest version of the Standard Model before you had neutrinos masses was just to say, well, neutrinos are massless because there's no such thing as a right-handed neutrino. So now that we know that neutrinos do have a mass, it means you have to have something else has to be going on. Either you have to put in some weirder couplings on left-handed neutrinos, some Majorana couplings to make the thing massive, or you have to introduce a right-handed neutrino field. And the problem with the right-handed neutrinos is that they don't feel any forces except gravitation. They only feel, you know, they have charge zero, they have no weak charge, they have no strong couplings. So, you know, they fit beautifully into the Standard Model. There's a hole right there exactly where they should be. So my guess is there probably are right-handed neutrinos, and it's very hard to say much about them because we can't really interact with them in any other normal ways.
Right.
But it's, you know, that these things, this smells a lot like the dark matter is starting to smell, in the sense that a particle which doesn't interact with anything except gravitationally.
Right.
And that.
So there could be some overlap there.
Yeah. So there could be. I mean, I think this is something I think particle physicists are often, a lot of them are well aware of, but they just don't. They tend to not like to advertise so well. Is because it's a fairly ugly possibility, in the sense that there is dark matter. It's a particle. If we could study it, it would tell us about particle physics, but you know, it has no interactions that we can manipulate or do. So we can't actually produce these things or see these things in a lab. The only people who are ever going to see them are the astronomers, and they're only going to see them gravitationally.
Yeah. Well, Peter, I don't want to take any more of your time. I really appreciate you taking the time to chat with me today and clearing this up. Thank you so much. If people want to find out more about what you're working on, where should they go?
So there's the blog I haven't really talked about. That's been very, very active, and haven't been doing so much recently, partly because I've been very obsessed with this twister thing. But so not even wrong. The blog I should advertise, and I think there's actually by now, 16 years of material of all, which I think there are all sorts of interesting things there. If you want something to see what I've been thinking about for the last 16 years, there's a few thousand posts at this point. And I will be writing more about twisters and Euclidean spinners there in the near future.
Yeah. Well, I mean, I appreciate, I've been following your work for, almost decades at this point. And I really, it's been really helpful to kind of ground me in a more scientific approach to the state of particle physics as opposed to the science fiction approach, which, you know, I know everybody craves. And so, you know, you, Sabina, a lot of the particle physics and even cosmologists and stuff who are directly interacting with the public and providing this information in an accessible way is a real service. So thank you.
Okay, thanks.
For me and for our viewers as well. You help sort of cross that bridge between the work that's being done so that the rest of us can understand it, and it's really helpful. So don't stop. But you're thousands in at this point, so you know I don't think you'll be able to quit.
Probably not.
Yeah.
Yeah. Anyway, it's kind of amazed me that when I started doing it, I thought I wouldn't last that long. I'd run out of anything interesting to talk about. But it's kind of amazing that it keeps being interesting. Things keep coming up, which are worth it.
Wonderful. All right. Well, I'll put some links in the show notes. Peter, thank you so much for taking the time to chat with us today, and good luck with your new theory and eventually figuring out the theory of everything.
Okay. Thanks.
All right. Take care.
Okay. Bye now.